Hi, in this video we're going to talk about how to find the oblique asymptotes that exist for some rational functions. I hope you've already watched the videos that show how to find vertical asymptotes and horizontal asymptotes for rational functions if those types of asymptotes exist for a particular rational function. Well, let me show you what I mean by an oblique asymptote. We mean an asymptote that is not vertical and not horizontal. Here's an example. You'll notice right here first that there is a vertical asymptote right here. I hope you know how to find it. It would be at x equals 4. I haven't drawn it in. But there is another asymptote that I really want to focus on. It's this line right here. Do you see how the graph seems to be approaching this line right here? This line that's at an angle. It's not horizontal and it's not vertical. And in fact, the oblique asymptote for this function, let me abbreviate it, oblique asymptote is at y equals x plus 1. Let me show you. Here's the graph again with the line y equals x plus 1 drawn in as a dashed line. And that's how we represent asymptotes when we're drawing a graph by hand. And notice how close the graph gets to the asymptote right here. The graph is approaching that asymptote, and if I went further out, the graph would get ever closer to the asymptote. Similarly down here. So when you're graphing a rational function by hand, having that asymptote is critical because it's a guide as to where the graph will be going. So a couple things come to mind. Number one, how would you know that this one does have an oblique asymptote? I showed you the graph, but if we were going to come up with the graph by hand, how would we know that it had one? And how would you find it? So let's start with the first question. How do you know that a rational function will have an oblique asymptote? Well, we look at the degree of both the numerator and the denominator. If the degree of the numerator is 1 greater than the degree of the denominator, you will have an oblique asymptote. So right here, second degree, and this is first degree. So now let's talk about how to find it. And it goes back to how do you rewrite a rational function so that it is in proper form, so that the degree in the numerator isn't larger than the degree in the denominator. And it's much like converting improper fractions into mixed numbers. So let's do it. We're going to divide x minus 4 into x squared minus 3x. And you can do this synthetically or with long division. I'm going to use synthetic division, I think, this time. So I will have 4 on the outside. That comes from my denominator. In the numerator, notice my coefficients are 1, -3, and 0. So I bring down my 1, I multiply and add, multiply and add. There's my remainder. So this function could be equivalently written as y equals, remember these are our coefficients of our quotient, that is x plus 1. It's really a 1x plus 1, but we'll write that as x plus 1 plus 4 over x minus 4. These two functions right here and right here are completely equivalent. Remember, comparable to writing an improper fraction as a mixed number. We're doing the same thing but with a rational function. Well, it turns out when we're looking at the function in this form, the equation of our oblique asymptote is looking at us. Consider what happens if you substitute in big numbers into this function right here. Notice if you put in 100, this would be a very tiny fraction. If you put in 1,000, it would be smaller still. And in fact, this fraction right here becomes insignificant as x gets very big or as x gets very small, like -100 or -1000. So this essentially becomes so small that the graph takes on the look of the line that would be y equals x plus 1. So you see right here, the equation of the oblique asymptote was just written as y equals x plus 1. Let's do another one. Let's find the equation of the oblique asymptote for this particular function. We have y equals 3 plus 2x minus x squared over x minus 2. So let's notice first the degree of the numerator is 2, the degree of the denominator is 1, so we expect to have an oblique asymptote. So let's rewrite this function in the other form. We're going to do our division. So I'm going to use synthetic division. I'm going to put 2 here. And my coefficients, I've got to take care, it's written backwards. I have a -1 as the coefficient of x squared, and then a 2 for the coefficient of x, and then 3 for the constant. I'll bring down my -1, multiply, and add, multiply, and add. And now I have the results. Notice these are the coefficients of the quotient, so I would have y equals -1x plus 0. I'm not going to write that plus 0 part. And then I have the remainder plus the remainder over the divisor, x minus 2. So let me just again remind you that this rational function is completely equivalent to this rational function. So our oblique asymptote is what we get if we discard the fraction here at the end. This becomes insignificant if the x values become big enough or small enough, and the graph will start to look like the line y equals -x. So let me write that. Y equals the opposite of x is the equation of our oblique asymptote. Here's the graph of the line y equals the opposite of x. And notice I put it in as a dashed line, as you will when you draw these graphs by hand. And here's what the graph actually looks like. And notice how it's hugging the oblique asymptote here and down here. Let's look at this one. The directions say to find the equation of the oblique asymptote, and you have a rational function, and you look and you see that the degree is 1 bigger in the numerator than the denominator, so you expect an oblique asymptote. So let's do the division and see what happens. I have -3 here, and my coefficients are 2, 5, -3, and let's do our division. Bring down our 2, multiply and add, multiply and add, and notice the remainder is 0. That means this function could be rewritten as f of x equals 2x minus 1. Those are the coefficients of the quotient right here and here, with no remainder, so I don't put plus 0 over x plus 3. I just have f of x equals 2x minus 1. These two are almost equivalent. Here's the way in which they're different. This one has a domain that is all reals except -3. This one does not. So you actually would have to say, hey, x can't be -3. Now these two functions are completely equivalent. So there's no oblique asymptote. In fact, let's graph this one. We know that we have a y-intercept of -1. The slope is 2, so up 2 over 1, up 2 over 1. So we know it looks like this. But notice I have not addressed this, that x can't equal -3. I don't have an asymptote there. I have a hole. This means right here at -1, -2, -3, I'm coming down to this point right here. That should be open right there. Let me just erase a little bit of it so that we can see that it is in fact open. Whoop. There. And now we have the graph of the function. It was actually almost a line, but with the hole in it. Now, was there a different way to get to that result? Sure. Right here at f of x equals 2x squared plus 5x minus 3 over x plus 3. If we had just factored the numerator, we know how to factor a trinomial like that. We'd have a 2x and an x and 1 and a 3 with the plus on the 3 and the minus on the 1. And notice that the x plus 3's cancel. And again, you get to f of x equals, f of x equals 2x minus 1, with a little disclaimer here that x can't be -3. But either way, we got the same result. So except for this situation where we got a remainder of 0 when we did the division, if you have a degree that is 1 bigger in the numerator than in the denominator, you expect to find an oblique asymptote. This was the exception. And by the way, I should make it very clear to the reader that I know that there is no oblique asymptote. It asked us to find the equation of the oblique asymptote, and I didn't explicitly state it. This f of x equals 2x minus 1 isn't the equation of the oblique asymptote, it's the equation of the function itself. Let's do one last problem. So here it is. We're going to find the equations of the asymptotes for this function. F of x equals 0.5x cubed minus 5x plus 2 over x squared minus 6x plus 5. Notice the degree of the numerator is 1 greater than the degree of the denominator. So when we get there, we will be looking for an oblique asymptote. But let's start with the other asymptotes, the vertical, horizontal, oblique. Let's roll through them. We'll start with our vertical asymptotes. Do you remember where to find those? We look in the denominator. If we factor the denominator, we'll have x minus 5 times x minus 1. And we'll leave the numerator unchanged. 0.5x cubed minus 5x plus 2. I do want to remind you that those will have vertical asymptotes at x equals 5 and at x equals 1, assuming that x minus 5 nor x minus 1 are also factors of the numerator. And you could confirm, in fact, that x minus 5 is not a factor of the numerator and x minus 1 is not a factor of the numerator. And you could do that just by substituting 5 into the numerator. You don't get 0. And substitute 1 into the numerator. You do not get 0. So, in fact, we do have vertical asymptotes at 5 and 1. I'm just going to write down horizontal asymptote so I know I thought about it. Remember that you have a horizontal asymptote if the degree of the numerator is smaller than the degree of the denominator, or if the degrees are equal. We don't have either of those cases, so I'm just going to write none. And now we're down to oblique asymptotes. And let me just remind you that oblique asymptotes are called slant asymptotes. You hear both very frequently. To find our oblique asymptote, we do need to do our division. I can't use synthetic division this time because our denominator is not linear. Notice we have an x squared there. So we need to use long division. So here we go. We have x squared minus 6x plus 5 into 0.5x cubed plus 0x squared minus 5x plus 2. So here we go. What do we need to multiply by x squared to get a 0.5x cubed? That is 0.5x, or 1/2 x. Multiply these together, so we have 0.5x times x squared. 0.5x times negative 6x is 3x squared, negative 3x squared. 0.5x times 5 is 2.25x. Isn't this good for us to do these decimals? And then we're going to subtract. So our 0.5x cubed minus 0.5x cubed is gone. We have 0x squared minus negative 3x squared. That is positive 3x squared. We have negative 5x minus 2.5x. That's negative 7.5x. Sorry, that looked a little bit sloppy there. And then we're going to bring down our 2 and keep going. What do we multiply by x squared to get a 3x squared? That's a 3. We multiply 3x squared minus 18x plus 15. And then we subtract. So we have, let's see, we have negative 7.5x plus 18x, that is 10.5x. We have 2 minus 15, that's negative 13. So our function could be equivalently written as y equals, I'm going to put it up here, y equals 0.5x plus 3 plus 10.5x minus 13 over, what's our divisor? X squared minus 6x plus 5. Again, this fraction right here becomes insignificant if your x values become big enough or small enough. And your oblique asymptote has the equation y equals 0.5x plus 3. But this whole function is equivalent to this function. And now notice we have the function written 3 different ways. Would have been nice if I'd written f of x instead of y. Let me erase that because that's going to bug me a little bit since it was presented with f of x. Let's write it that way. There we go. So now we have the equation of our oblique asymptote is y equals 0.5x or 1/2 x. If you're graphing that, maybe you prefer to use 1/2 plus 3. I know I haven't talked about how to come up with the graph of the function, and that will be another video. But I do want you to see how the asymptotes relate to the graph. So here are the asymptotes that we found. A vertical asymptote at 5 and at 1, right here and here. And this line right here, it has a y-intercept of 3 and a slope of 1/2. So you would draw those in as a dashed line. And now let me show you how the graph would look. And here's what the graph looks like. Notice how close the graph gets to the asymptote in some of these. And if in some of these places right here, it was almost resting on it. And if you went out far enough, this graph would start to look like this line. It would be hugging the line pretty closely. And notice that's the case for all of the asymptotes. The graph is approaching the asymptotes. Your asymptotes will be your graphing guides. That's why it's so important that you know how to find them.